Dear all, I'm pleased to welcome you all to today's talk by Professor Dr. Adrian Jäggi. As you can see, we are still in the online modus, unfortunately. We, of course, all hope to go back to the regular talks sometimes. I think there is some hope that this will be possible maybe towards the end of the year or maybe even in summer. We don't know that, of course. Before the talk, I would, of course, like to introduce to you Adrian Jäggi, who I know also personally for a very long time. So Adrian obtained his studies in physics, astronomy, and mathematics, did his studies at the University of Bern in 1996, and then in 2006, he obtained his PhD in astronomy at the Astronomical Institute of the University of Bern, where on the thesis subject was the pseudo-stochastic orbit modeling of low Earth satellites using the global positioning system, the GPS, that certainly all of you are also using all the time. He then was a research associate at the IUP, where he did various research related to orbit determination, and he was also involved in the operations of the Center for Orbit Determination in Europe. He then became a lecturer, and in 2007, still at IUP, and then in 2007, he became the Carl von Linde Junior Fellow at the Institute for Advanced Study at the Technical University of Munich. And there he studied the global gravity field recovery, which is part of the research already that he will be talking about today. Later, he was a senior research scientist at IUP, and then in 2012, he became professor and director of the IUP, the position that he is currently holding. And during that time, between 2015 and 2020, he was also our well-known director of the association Pro-EC. Therefore, it's also a special pleasure, of course, to have him here today as our speaker. Adrian Jäggi holds also many more positions and appointments. It's maybe worth mentioning that he's the chair of the directing board of the combination service for time variable gravity fields. And this is something he's also going to address in the second or in the last part of his talk. And here there is another link to EC in the sense that they are supported by EC teams in this activity. Second, he's also president of the Commission 2 Gravity Field of the International Association of Geodesy. And before he starts, allow me to also make a personal remark here. It was actually him who taught me to learn doing orbital numerical integrations of orbits. This was at the time where I was myself a young student and Adrian was the assistant. And this was really an extremely positive experience for me. And this is not even all, because Adrian was actually my predecessor before me doing observations at Zimmerwald Observatory. And so he could, thanks to him, I could then also enter the world of astronomical observations. So in that sense, Adrian, thank you very much for all these different aspects. And we are, of course, now looking very much forward to your talk. Please.
Yeah, thanks a lot, Christoph. And of course, also from my side, it was a pleasure to introduce you to its celestial mechanics and astronomy. So it paid off very well, I think. So that's very good. And I would like to welcome all of you to my talk, also from my side. I will speak about exploring the Earth's time variable gravity field using satellite observations. And I would like to mention here that I will give this presentation also on behalf of a larger group of people assembled within different initiatives that are receiving funding from the European Commission and from EC, and I would like to acknowledge this. You see some logos in the bottom part. I will come back to these initiatives a bit later on in the last part of my presentations. And I would also like to acknowledge all the contributions that I received here entering into this presentation that I will show you in about the next 60 minutes or so. I will start my presentation with a very brief overview on what we are actually interested to study a bit in this talk. We'll then address how we measure these signals, and will detail what kind of signals actually we are here interested in, and will then, as already mentioned, conclude with the role of some of these mentioned European initiatives that play, in my opinion, an important role in this context. So let's start, and it's about all the Earth's gravity field, of course. And we all know, as we have learned it in school, that the gravitational pull at the Earth's surface is about 9.81 meters per second square. That's when assuming a mass point or homogeneous sphere with an equal distribution of the density. And some of us probably also know that this is a somewhat a bit simplified picture. If we have a little bit a closer look, because the Earth is rotating and therefore oblate, the surface acceleration is varying between boundaries of, let's say, 9.78 meters per second square and 9.83 meters per second square, showing this pattern that you see here. If we subtract this pattern, then we are getting a bit closer to what we are actually interested in here in this presentation, about all the variabilities that remain here on the spatial scale, with variations of about plus minus 0.0004 meters per second square. And as you see, these are already pretty small numbers. We will use in some of the following plots a little bit different unit. We use sometimes so-called milligauss. This stands for Galileo de Gauss, which is a special unit 10 to minus 5 meters per second square. Just to make these numbers a bit more handy, this is about 1 millionth of the pull at the Earth's surface, this 1 milligauss that you see here. So let's start to have a look at these maps. These are so-called gravity anomalies that are shown here. And this is per se an interesting topic already. And there were also former presentations in the frame of ProISI, for example, by Professor Rainer Rummel, about the determination of this static part of the Earth's gravity field. That's actually not what we are really very much interested in this presentation here. And I would like to show you what we are interested in. We are interested in the time variable signal. And in order to illustrate a little bit how large these signals are, I will show you first this map here in March, as you can see it here, of a certain year. And now I show it in September of the same year. And switching forth and back a little bit, you will probably not be able to really see some differences. Even if you would have the sharpest eyes, I believe you would not see any differences, because it's a rather small effect and a rather small signal that we are interested here. And already here, the signal is of the static field is pretty small. You see here we are now in these units of milligauss, plus minus 100 of these milligauss, and we do not see any time variations directly. So let's have a look at the differences of these maps, subtracting the two maps, and then we get a green map. And you can see here what green means. Green means either it's totally zero or at least very, very small, apparently, when we look here at this plus minus 100 milligauss scale. So let's have a focus, shorten it to plus minus 1 milligauss, and then we start seeing something. What we start seeing here is basically noise, because these are measured data, they are not error-free. And these noise patterns here, they are revealed. They are not really what we are still interested in. They are just annoying somehow. So we need first to get rid of them. And I do this here by somehow cleaning the window, so to say, cleaning this pattern, this illustration here. And then we get rid of by this cleaning. Cleaning means some type of filtering of this pattern that you have just seen here. And then we are again back at the green map. So green still means zero. So apparently we are looking for quite small effects. We need to narrow down again by a factor 100. In total, we have now already narrowed down to by 1/10,000. And then we start seeing some time variable signals between these 2 months, September and March. And this is basically the topic of this presentation, where I would like to start explaining a little bit how we measure these things from space on a global scale. So let's start about this. How do we measure these changes? And in principle, the basic idea, we can go back very far in time, back to Newton. When looking at one of his famous drawings here from his book, The World Systems, then we see a famous thought experiment that most of you probably have already seen at some point. Let us imagine that the scientist is climbing up a hill and throwing a stone away with a larger and larger initial velocity. At some point, in principle, this stone should then circle around the Earth. And by this thought experiment, Newton in principle has already taken up the idea of these artificial objects, point masses, mass points that are circling around the Earth, of course, satellites that we are currently and nowadays observing with great interest, because we can learn quite a lot by studying, for example, the trajectory of such a satellite in order to infer some information about the attracting body, which is here in the focal point of this ellipse. And we can do this by either directly somehow measuring this trajectory, or, for example, measuring the velocity, that's the green arrow that is shown here, or also the acceleration, which are the magenta arrows. And this is what is currently being done, of course. We have here a typical picture how such satellite ground tracks look like when we have orbital altitudes between about 200 and 500 kilometers. And we see that after a very short time, we have already quite a good coverage of the surface of the Earth with measurements. And if we wait just a bit, here it's shown after 10 days, a fairly dense coverage is obtained. And if we just wait long enough, this will get denser and denser. And the picture is now shown for 30 days, about 1 month, which will be the typical time period where we try to derive this gravity information in the form of so-called monthly snapshots. So perfect test masses that are sensing the irregularities of the Earth's gravity field, and we are interested to observe their motion. This idea has been followed since the beginning of the space age. What you see here is a photograph of the first artificial satellite orbiting the Earth, the Sputnik satellite from the former Soviet Union. Those of you who are familiar with the night sky will immediately recognize that this is the Big Dipper that you see here, the famous constellation, and here you see the orbital track, the illuminated Sputnik satellites, and astronomers, of course, and in particular also geodesists have started observing these satellites by taking photographs and measuring the orbital position with respect to the sky background, with respect to the stars, in order to do orbit determination. So orbit determination, in fact, is the key access to these type of measurements. We are interested to study orbit perturbations, and let me spend a short moment what orbit determination means. It means that we determine elements that are describing a satellite orbit. Typically, we are using Keplerian elements, where two of these elements, the semi-major axis, that's half of the maximum diameter in the ellipse, and the numerical eccentricity describe the shape. So eccentricity, how deviating it is from the circle. Then we have two further elements, orbital inclination, which describes together with the ascending node, right ascension of the ascending node, how the orbital plane is oriented in space. And within the orbital plane, we need one more angle to orient the ellipse and one last element to define where the satellite was at a certain initial time t0. And these classical Keplerian elements, they would stay constant for all the time if we would have a perfect mass point, a spherical Earth with homogeneous density. As we already have seen at the very beginning, the Earth is oblate because it is rotating, and therefore we are expecting perturbations in these orbital elements. In particular, we are expecting that the orbit is precessing. A secular precession of the satellite's orbital plane is expected. You see this illustrated here in this graph, that this orbit is somehow moving, and this is basically reflected by one of these elements that I have just mentioned before. And I show you here how this would have looked like for the Sputnik satellite. You see that this is a huge effect actually. After very few days already, after 5 days, it is shown here, we already have a change in this node of about 15 degrees. So it's a large effect that can be relatively easy observed after a very short time of observations, and therefore observing satellites has allowed to determine the Earth's oblateness based on very short time spans of observed orbital arcs already, and by this really revolutionizing the work of decades of terrestrial surveying done before in order to, for example, define the shape or measure the shape of the Earth. So satellites are very interesting, and the basic principle, in fact, is more or less identical still today. The only difference is that we have so-called dedicated gravity missions nowadays with specialized tracking technologies that pave the way for our picture that we have currently of our planet Earth. And it all started in the year 2000 with the first demonstrator mission called CHAMP. CHAMP stands for Challenging Mini-Satellite Payload. It was a mission operated by GFSat Potsdam, that's the German Research Center for Geosciences, lasted for 10 years, and it demonstrated the high quality and valuable use of GPS. As Christoph mentioned already at the introduction, GPS is a key technology in order to follow trajectories of any moving objects, and this is addressed in the literature as the so-called high-low satellite-to-satellite tracking. I will briefly come back to this a couple of slides later to explain a bit more on this. Then we have a second mission, which was really very important, still is today, the GRACE mission. GRACE stands for Gravity Recovery and Climate Experiment. It's a NASA DLR mission that has been launched in 2002 and lasted for 15 years, a very long time, dedicated to measure the time variable gravity field. So it will be in the focus of this presentation. There were two satellites following each other on the same orbital track. And of course, I will say a little bit more about this in a couple of minutes. There was an ESA mission also in the game, the so-called GOCE mission, Gravity and Ocean Circulation Explorer mission, launched in 2009 until 2013. It was lasting and delivering science data. Those of you that have followed already several ProISI talks might remember that there was the presentation from Rainer Rummel exactly about this mission, which was dedicated to derive the static part of the Earth's gravity field, so all the not very quickly changing spatial features that you have seen at the map at the very beginning of my presentation. And the last mission at the moment in this context is the follow-on mission of the GRACE mission, so-called GRACE follow-on, again a NASA GFC mission launched in 2018. Nominal lifetime will be 5 years, but of course we all hope that similar to the GRACE mission, which lasted for 15 years, that also the GRACE follow-on mission will hopefully last much longer than the year 2022 that is illustrated here. What is in common in all these missions is that we would like to try to measure the Earth's gravity field, and we model this by the potential function. And that's basically one of the only formulas or so that I included here. I would not really like to discuss the formula, but try to illustrate a little bit what we mean with this. We have this quantity that we want to measure, and we develop it into a series expansion, a so-called spherical harmonic series, up to a maximum degree, which is illustrated here, Lmax. And in this rather complicated expansion, there are some coefficients. They are denoted here by C's and by S. And these are actually the unknown parameters that we are interested to determine from the different tracking technologies. And I think it's most illustrative if we just look at the picture that we see here on the slide. This picture will show in terms of so-called geoid heights, that's an equipotential surface in the Earth's gravity field that is illustrated here, how this changes when we just increase this maximum resolution here. And I will do this, start here with the picture up to degree and order 3, so a very low and modest resolution, more or less similar what has been possible, let's say, with the old Sputnik data at the very beginning. And I will now improve this to 4 and 5 and make some larger jumps, go to degree and order 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And now, to not be too lengthy, I will make huge jumps, about 50 degrees, degree 100 or 150, 200, and 250. And this 250 that you see here in this table, that approximately corresponds to the resolution that is possible or was possible for this GOCE mission that I've briefly mentioned for deriving the static part of the Earth's gravity field. You see that this implies that we have more than 60,000 of these numbers, of these coefficients that need to be determined as unknown parameters. And with the number or the maximum degree is also implied a certain spatial resolution here in terms of so-called half wavelengths of about 80 kilometers. That's the best what can be derived in terms of static field from satellite data alone. If we are interested in the time variable field, then we need to be more modest. It's not possible to go up to that high degree and order. We are going up at best, maybe something between degree 60 and 100, somewhere in between. So we are rather speaking here about resolutions that I will show in the following in the order of, let's say, 300 kilometers at the very end. And how do we do this? We are interested, as already mentioned before, to measure the motion of the satellites. And this can be done by different and various tracking technologies. We have GPS, the Global Positioning System, for example. These are satellites that are transmitting all the time various signals, in particular also signals which are interesting for scientific applications, and they can be recorded by dedicated receivers which are on board of these satellites. The principle is a bit similar as in your navigation system in the car or in your smartphone, but there, of course, not all of the interesting signals can be recorded, and therefore you have to live with a little bit less precise results. But in principle, it's the same way of data that are being used for this purpose here as well. We have also on ground so-called satellite laser ranging stations. They are on astronomical observatories. They are shooting short laser pulses to the satellites, and they are sent back to the stations, and they allow distance measurements. I will come back very quickly also on this, both together allowing us to achieve about centimeter precision or precisions for the orbital trajectories. So we are interested to follow these irregular trajectories that the satellite is performing here on this irregular Earth's gravity field. If we have several satellites in place, and we have seen that the GRACE mission is a constellation of 2 satellites, then we can already improve the situation quite a bit by forming differences and studying differential motions. About 1 order of magnitude can be gained by this, but the ultimate improvement is by exchanging actually signals between these 2 satellites. And this can be done in the GRACE mission with superb micrometer precision. That's really great. This is the diameter of a human blood cell, a micrometer. And on the latest GRACE follow-on mission, there is even a laser interferometer installed, which allows to go very close down, even to nanometer precision, which is stunning. So it's just unbelievable, I would say. A superb observable that is very valuable for this gravity field studies. Let me first, before coming to a bit more to these dedicated measurements, to the background that I've started with. Of course, as I'm from the University of Bern, I have to mention a couple of words about our activities in this domain as well. So, for example, satellite laser ranging is being performed at the Swiss Optical Ground Station and Geodynamics Observatory in Zimmerwald. That's an astronomical observatory that we are operating together with the Swiss Federal Office of Topography, where such distance measurements to dedicated satellites equipped with reflectors are performed in a fully automated mode, 24/7 operations with a large telescope, this 1-meter telescope that is used for both satellite laser ranging and the optical astronomy as well. It's, by the way, one of the most productive SLR stations worldwide. At least on the northern hemisphere, usually it is the most productive one. There is just one nasty station on the southern hemisphere in the Australian outback, where they have 400 days per year, nice and brilliant weather, whereas the weather in Switzerland, well, you all know, it's far from being perfect. Then also a short word about the GPS analysis. There is the University of Bern, a so-called Center for Orbit Determination in Europe that's operated also at the Astronomical Institute, where all the different global navigation satellite systems are processed and high-quality products are derived, for example, for the Global Positioning System, GPS, and the European Galileo system, every day on a routine basis for all the scientists really available to do their interesting studies. And it's always good to remind that all these type of applications that we are speaking here, they would simply not be possible without having a technology like GPS with all the products on precise orbit information, clock information, all what is needed to process these data. Good. And last commercial, and then I will come back to GRACE. Of course, one needs dedicated software packages in order to all do this processing work. We at the University of Bern have been involved, or actually initiated and still develop until today, the Bernese GNSS software, a scientific package for high precision analysis of the various space geodetic data. We use this also for the GRACE processing that I'm speaking here in this talk, and it has been developed since many decades meanwhile, and is meanwhile also being used by more than 700 institutions worldwide. These are other universities, research centers, federal agencies for topography, etc., etc. Good. What we do, we need to model the motion of the satellites. I already mentioned this. And of course, in physics, the motion of a satellite is described by an equation of motion. So we have to solve such an equation of motion. And we see here illustrated for this first CHAMP mission, this Pathfinder mission, that this might be a little bit a complicated trajectory. You see here all the ups and downs that we need to somehow describe. It's actually the goal at the very end, by analyzing the trajectory, to reconstruct even some of those that are maybe not perfectly known at the beginning. We do this by numerically integrating the orbits with hopefully high precision, and we need to take into account various force models, where I will not go through the full list here, but just to mention that there are many different background information that needs to be taken into account. Maybe just highlighting one, because we can show a nice movie about this. For example, tidal effects. The very fast varying time variations in the Earth's gravity field, typically something that needs to be modeled and needs to be taken into account to achieve very high, precise orbital information. So the orbits are the key quantity, but the orbits itself, the tracking technologies are not good enough to really go for these monthly snapshots in the Earth's time variable gravity field. So we need the differential motion, and we need to measure in the satellite, with the satellites, this differential motion, because here the principle is illustrated, of course not plotted according to scale. This is the Mount Everest, and the GRACE satellites are flying a bit higher. They are at about 450 kilometers altitude, but for illustrative purposes, you see here that they are experiencing different accelerations, different attractions from this mass anomaly here from the Mount Everest. And this has a consequence, of course, on the intersatellite range. It will change. And it will change in a very characteristic way when the satellites are flying over this mass anomaly and exactly measuring this very characteristic distance chain with ultra high precision. This gives us access to this information we are actually looking for. Because, as already mentioned, we can do this on, or it can be done on a distance difference of about 220 kilometers with this micrometer precision, which would be in these units above here, the 12th digit is the measurement precision that you see here, and that's far more precise than all what would be possible from GPS or SLR alone. And therefore, all these different techniques are needed to be processed together and used together to have the full picture here. Of course, when processing these data to a time series of monthly gravity field solutions, so that's what we are aiming for, one can imagine that this is probably not so easy as it might maybe sound at the first sight. So it's a rather challenging process, because there is an interaction of multiple instruments that needs to be taken into account. These instruments have all different noise characteristics, things that are actually quite important when exploiting these data. There are some environmental disturbances, for example, affected by the ionosphere, or there are atmospheric effects, oceanic effects that are all taking place and need somehow to be considered. And there are the tidal effects already mentioned before. So it's a rather complex process. And still today, more than, meanwhile, 19 years after the launch of GRACE, Still, there is not one true solution how this should be done in the best and optimal way. Instead, there are many different groups doing this processing, and I will come back to this at the end of my presentation, where we've tried to find, nevertheless, some way to deliver to the community, hopefully one consolidated solution about these monthly snapshots. And just to mention it very briefly, it did not get easier with the new GRACE follow-on mission. The data are so precise that currently no scientists on the entire planet is really able to fully exploit these data, because many of the background models in particular that are needed for doing this exercise, they are simply not good enough at the moment to really exploit this measurement precision. So let's come now a little bit to what changes actually can be measured with these data. And for this purpose, we will have a look again at our map here of the time variations. And before starting with this, I would like to make you aware that we now have here a little bit a different unit on the color scale. You see this. We are addressing these changes now in units of so-called equivalent water heights. This is a little bit the more handy unit, so to say, where one can try to imagine a little bit better what this is, and it has to be read in the following way. If you have here, for example, a plop over the Amazon basin, more or less white, you would read here that this corresponds to 20 to 25 centimeters of equivalent water height, and you can interpret this in a way that if you multiply this with the area where you are looking for this, then you get directly a number in volumes, in cubic kilometers, and you can relate this to how many gigatons in water this would correspond, so to say, to make this gravitational effect on the satellite. So that's a bit the more convenient unit, how one is addressing these signals here. And we will now start having a look at the most pronounced signal that one sees when looking for periodic variations. These are over the large river basins of the planet, and the largest one is the Amazon basin. And what we see there is the movement of water masses. So there is in the rainforest, one can imagine there is a lot of water which can be moved around, and this is exactly what these GRACE follow-on type of missions are able to detect or to monitor. You see here an animation over a couple of years, how this is going up and down, and this is showing you where there is more water and where there is less water. In this color scale here, blue means more water, and redly means less water, and you see here some type of seasonal variations in this river basin, also reflected here the seasonal cycle in this time plot, in this time series plot here. So what GRACE and GRACE follow-on are basically able to measure on a global scale with a certain modest resolution. I would like to point out this here again. So we are not speaking about tiniest variations on the kilometer scale or something like this. It has always just a resolution of about, let's say, 300 kilometers, but there one is able to see changes, for example, in the global water cycle. So basically, in what we all have learned at some point in elementary school, I believe, that, for example, over the oceans, water is evaporating, and then there is precipitation over the continents, for example. Some of the water is flowing back into the sea, or it's going into the groundwater or soil moisture, or some part is maybe also stored here in the form of snow and ice in the higher altitude regions. So this entire cycle, which is going with the seasonality, that's what GRACE basically can see on relatively large scales of 300 and more kilometers. This is addressed as changes in so-called total water storage. So it's important to emphasize GRACE cannot really detect the absolute level. It can just detect the changes, how much this total water storage is changing. And this total water storage that can only be measured on a global scale from space with the GRACE follow-on technology. So from inferring gravitational changes, from studying motions in satellite orbits. Of course, interesting is always then to further distinguish this into the different compartments. For example, to tell how much is the groundwater, for example, changing, or the surface water, or the snow water equivalent, or the soil moisture, all these different compartments that make in the sun, as it is shown here, the total water storage changes that can be derived by GRACE. But all these things, in particular also the accessible water, just as an example, that is accessible to us on the surface or near the surface, to distinguish this, one will need additional measurements. So that's not something that the satellites, of course, can distinguish. They do not know if a change is coming from changes in groundwater or surface water. They just see the total that is all changing here in the vicinity of the Earth's surface. Good, let's have a look at some of the other signals. Most pronounced are always the signals, of course, in the polar regions, because this is obviously linked to climate change variations. So let's have a look here at Greenland, for example, and here trends are now shown. So it's now not a periodic signal, but some long-term changes that are ongoing. For example, here in Greenland, predominantly, as the blue color implies here, in the coastal regions, at the coastal regions of Greenland. And there I would like to spend a couple of minutes showing you some of the latest series that we are producing within one of these initiatives that have already been mentioned implicitly, namely for the different drainage basins of the Greenland ice sheet. You see here that Greenland is large enough that GRACE can distinguish between different regions here. And what is shown here are now all the different mass change trends for most of the basins. The space was a little bit too small to put all of the 8 basins here on the slide, but at least 6 I managed to put on here on the different sides of Greenland. And what we basically see is that for all the basins here, there is a significant mass loss that is observed by GRACE. I must emphasize here that this is already quite a heavily processed plot, or the plots that are shown here are already heavily processed, because again, GRACE cannot really distinguish between different signals that are ongoing in parallel. And there is, for example, also a land uplift in these regions, and GRACE can just see the total. But with other measurements and models, one tries to reduce this land uplift effect, for example, to separate the ice, and then various measures need to be taken in order to convert this really mass change series in gigatons, and that has been done here. And if one sums this all up together, one receives a mass loss of a linear trend of something around order of magnitude 250 gigatons per year. And you see this is not going in the same way for all the basins. Some of them have larger trends, some of them have smaller trends. Largest ones are, for example, here on this western part of Greenland here with basin number 8, where you see a very pronounced negative behavior with this linear trend. And in fact, you already see here that it's even more than just linear. It's also a quadratic behavior that is can be seen here. And I must maybe also emphasize, if you look at the numbers and would compare it with other studies or so, I must mention here that there is also a quadratic term fitted, and then this is the linear term that remains that is here. If one would not do this, the number would even be larger somewhat than the 250 gigatons. Now, this is a huge number, and it's very difficult and hard to imagine maybe how much this actually is. So we do not have a feeling, of course, for these type of numbers. And in order to illustrate this a bit, we made an attempt at the Festival Bernimal, for example, in summer 2019 to put an experiment there on the Bundesplatz with a quiz, where we put 1 cubic meter of ice that we ordered here for this experiment. And we were asking the people that were passing by how many of these blocks are melting in Greenland every second. Of course, if you know the answer from the previous slide, you can calculate this now, but it gives maybe a little bit an impression how much this is. And the answer is that about 10,000 of these blocks are melting in Greenland every second. So that's the frightening number that can be seen here. And thanks to this orbital technology and the analysis of these intersatellite ranges, we are able to monitor this more or less continuously if we have data available to tell us how exactly this is changing over time. And the specialists in the field that are then the cryospheric experts can then try to interpret all these changes and maybe also try to explain some of the natural variations and to separate the natural from the less natural variations. The same content of information is put here in this movie. That's a nice official movie from NASA, where this is also illustrated here. Accumulation in an accumulated way, it's just summing up in the movie, and overlaid is also our flow velocities of the glaciers. That's of course not coming from GRACE. These are other technologies that are used here for this purpose, where the scientists are of course trying to bring together all different type of data together and to see if they are ending up in a consistent picture to understand all these ongoing changes. And similar pictures can be shown also for Antarctica, for example. Antarctica is much larger than Greenland, so there GRACE has the possibility to see some more of these drainage basins. And we see rather similar effects to some extent. For example, also some of the regions which are experiencing a very heavy ice mass loss, for example, here in the Western Antarctica regions close to the Antarctic Peninsula. But there are also some other regions where there is even actually a mass gain in some of the basins, for example, this basin that you can see here. But in total, it's nevertheless, overall, it's a dramatic mass loss that is observed and can be continuously monitored by satellite gravimetry missions like GRACE and GRACE Follow-On. Of course, we are fully aware, and in particular also all the ProEC audience, if you have listened to the presentation from Annika Snav, it was I think in October 2019, that this heavily impacts, for example, also sea level rise, one of the largest threats that is ongoing due to climate change. We see, for example, if the entire Greenland or Antarctica would melt away in a worst case scenario, so to say, this would have dramatic impacts on sea level rise, about 7 meters for entire Greenland or about 60 meters for entire Antarctica. So GRACE is here the tool that weights the ice sheets and identifies the loss and gain on a regional level and allows us to also assess how much this at the very end also contributes to sea level rise. So it's some kind of a monitoring system that is most important to deliver here numbers. And this is then the consequences in the media, of course. This is omnipresent from time to time, always. This is being recapitulated and being monitored. You see here, for example, that we have at the moment about 1.5 millimeters or so per year coming from the mass loss, from the ice mass loss of the glaciers and from Antarctica, contributing a significant part to the total effect, a little bit less than 4 millimeters per year. That is also mainly coming from temperature changes in the oceans. And of course, this is really dramatic. One can easily imagine, depending the way how this will develop, that easily millions of people will be affected, depending how large this will really be at some point. So a very interesting technology, generally speaking, for the study of the availability of water. You see here a rather recent study from NASA researchers where they tried to quantify and also to address all the different trends that are emerging in the water distribution and the water availability. A lot can be detected, for example, where there is ongoing groundwater depletion or similar effects, or also drought effects that can be prominently seen in these kind of measurement data. And for example, concerning droughts, this is maybe a good comparison here, that when we go for a famous region where an ongoing drought is present, the California region, that maybe in the middle of the 19th century, it was rather the hunt for gold that was relevant in the western part of the US, and maybe nowadays we can say that more or less the hunt of water is somehow equivalently important than it was gold for the very old times. And this also is something that is prominently sometimes also in the media being taken up. And you see here one example from a study, how one can imagine that these data are somehow helpful. One can observe the actual water storage variations in the GRACE data. This is the top figure here, showing not only trends, but also natural variability, seasonal variability, and one can try to deduce somehow a normal range of water storage variations. And the difference basically is then what matters in the sense of warning for droughts, the difference to normal dry conditions, where one can see, for example, that at some point here where this entire curve is going down a bit, probably some kind of a drought begins, and at some point maybe it stops again, and there is a deficit magnitude that can be quantified thanks to the measurement principle of these satellite missions. That's one of the extreme cases, which is very interesting, but rather long-term effects. Droughts are typically going on for longer time intervals. And there is the other extreme where one is also trying to exploit a little bit the GRACE data. That's maybe at the moment still in a bit experimental status. But as the initiatives we are involved in also try to contribute to this a bit, I would like to address this for a moment. If one looks here over Europe and thinks about floods, then maybe the picture looks not very promising at first sight, but nevertheless, let's have a look at it for a couple of minutes, because when ongoing flood events are there, then also water is redistributed in an unfavorable way for the people that are affected, of course. And if there is more water somewhere, there is more mass, and maybe one has a chance to see it in the data. So before doing so, we have to quickly remind us that there is also a problem involved with going for such short-term effects. And the problem is the ground track coverage that I've mentioned at the very beginning of the presentation. We always need to wait quite a long time actually to have a sufficient ground track coverage to have at least this modest resolution that we currently are able to exploit in GRACE data. So usually we need to wait 1 month. But floods, of course, are very short-term effects. So we would be interested to go to much short timescales, for example, to 1 day. But you immediately see from the picture we have a problem there. We don't really have the ground track coverage. On the other hand, we also know that usually the time variable Earth's gravity field is not arbitrarily changing from day to day. So we know a little bit what the normal range of variability is, and we can try to take this somehow into account. Indeed, it's possible to have something like daily solutions with much less good spatial resolution, but nevertheless, that allow to do studies in this respect. But we always have to remind ourselves we cannot have both. Either we have good spatial resolution, bad temporal resolution, or good temporal resolution and bad spatial resolution. So it's a little bit like Heisenberg's uncertainty relation here adapted to satellite motion, if you like. Good. There was one experiment that we did in the frame of one of these initiatives where we had a look at this, and one group in the consortium from Austria, from Technical University of Graz, actually pioneered in this type of solutions by providing daily solutions. And what you see here in this movie is what remains after subtraction of all the well-known signals, so to say. Mostly what you see is noise, but sometimes when you will look at this point that is illustrated here, when also this line will go to this peak, then you will see that there is a little bit more blue than usual. And these are the kind of signals that one tries to hunt and exploit a little bit, because they could give access to maybe interesting applications in the future of these GRACE and GRACE follow-on tracking technologies. And the question, of course, is this really helpful? Yes, we can already substantiate a bit that it might be helpful. So the answer is not yet fully consolidated, but potentially yes, because one can imagine it in the way that if there is a lot of saturation in the soils with water, then maybe this can favor the development of floods if the water can no longer go into the soil and needs just to be distributed over the areas. And therefore, it might be worth to check unusual developments in total water storage that may serve in the future maybe as an additional indicator for the potential development of floods. And that's an interesting application. The thought is not new. One has seen it for a long time already with its monthly solutions, that if one constructs certain indices which somehow give the potential whether there is potential for some flood events, that this indeed has quite a bit of correlation with actually ongoing floods. This has been shown for a long time ago, that there might be a correlation and that there's maybe worth to further look into this. These kind of data were of no use so far because all these monthly snapshots, and they are not really interesting for going to really something like forecasting applications. In order to be useful for this, one needs to have this information in near real time, and in particular with significantly improved, speaking, the daily resolution. And one could experiment around with this in this initiative, and indeed it was possible to show at least that for some of the major flood events in a certain basin, it was the Danube Basin where this test has been performed, there was indeed also for quite some cases a correct positive correlation that some unusual developments in the build-up of total water storage could be detected before an actual flood then could happen. And maybe at some point, at some point in time, if this information will be available routinely in near real time, this might be an interesting quantity to check, because now our technology can really sense the total water storage as it is in a basin present. And some of these large-scale floods, maybe there is a potential to be a little bit earlier aware when there could something really happen. That from the technical side of the satellite processing, this would be possible. This has been demonstrated in the very final phase of the GRACE mission, a situation where the data was already very challenging to process, but there a near real-time test has been performed by providing these type of variations, actually in near real time with a delay of less than 1 day, which has not been shown before. And we all hope that with GRACE follow-on now being in orbit and most of the initial data problems being solved or understood, that also these type of data will be retaken up to be generated and then maybe fed into such kind of monitoring applications. Because the conceptual idea that could be followed is that nowadays very often it's still the case that an alarm, for example, about an ongoing flood or so is just happening if the flood is already there, and then it's maybe a little bit late. And then once this has been done, then an entire chain of actions will be performed. There are dedicated centers, for example, at DLR in Germany, there is a Center for Satellite-Based Crisis Information, which takes actions then tasking all the different remote sensing satellites that are needed to get data, to produce maps that can then be delivered about the flood extent, for example, to the rescue teams. And if one would be aware a little bit earlier that something might really happen, then all the specialized satellites, where there are not so many that the full picture of the entire Earth is available all the time, they could maybe program them tasks already a little bit earlier. So this might be one of the ideas for the future, that some of these alarms could be taken earlier thanks to gravity-based wetness indicators, so to say. So these were some past initiatives or some past experiments. I would like to close my presentation or slowly come to the end by explaining a little bit about European initiatives where our institution is currently being involved and maybe what kind of future perspectives they will give us. And I would like to start here with the plot that the GRACE project, it's a NASA Germany project between NASA and the German Center for Geosciences, basically consists of 3 so-called SDS, Science Data System Analysis Centers, that's JPL, and CSR, that's the Center for Space Research, University of Texas in Austin, and GFC. But since the start of the GRACE mission, there were much more teams actually exploiting these data, and some of them are really generating impressive solutions of very, very high quality. And currently we have 5 of these analysis centers in Europe, and we have even more if we go also further away to China, for example. Also in China, we have currently about 5 analysis centers. And one of the idea would be to bring these centers closer together, to act, so to say, as one virtual center, if you like, to profit as possible way from each other, to exchange all the tiny details about the data processing. This was exactly the idea of a Horizon 2020 project that the University of Bern coordinated between 2015 and 17. It is this initiative that paved the way for the current initiatives, I would say, and has even been nicely acknowledged also on the US side by mentioning it in the NASA's decadal survey. And based on this, we are currently continuing with parts of the operations of the XCM project in the so-called COSG initiative. That's an activity of the International Association of Geodesy, again coordinated by the University of Bern. And you see the similarity in the logos. That's of course on purpose to show that this is going in this direction any further. And we also initiated to have a direct follow-up of the XCM initiative with the same gravity core team as already in XCM to initiate the so-called global gravity-based groundwater product. It's a currently ongoing Horizon project that is coordinated by GFC in Potsdam. And I will briefly address for all three a little bit what has been done and what we are doing. The XCM initiative, the idea is very simple. So we have this bunch of analysis centers. They're all doing great work, but the solutions are fairly different still. And maybe not so much in terms of signal. We hope that they are all sensing the same signal, of course, but in particular in terms of noise. And still today, the differences are quite large actually in terms of noise. And therefore, the idea was to bring this together, bring the knowledge together and try to come up with an improved and consolidated product that is to some extent, hopefully integrating the strengths of all the individual analysis centers. And this XCM combination has been demonstrated in the frame of this initiative, and that's exactly what is now operationally being continued in the frame of this combination service of time variable gravity fields, COSG, under the umbrella of the IAG's International Gravity Field Service. So we now speak of the COSG combination, and I would really like to acknowledge here in particular ISI, which supported us a lot in this respect by allowing or granting us an international team where we could exactly do this and bring this to life. So if you are interested in this, I would like to mention here that we have a website where there is a lot of interesting, hopefully interesting information. And in particular, there is also a plotter that can be used to make some kind of these plots that I have shown here in this presentation also by yourself by just clicking, and it's relatively easy to use this tool. The products that we are delivering are these monthly snapshots, so one product. The hope is that at some point this will be the standard product for the users, and we have done this for the entire GRACE and GRACE follow-on period. You see here the distinction. GRACE part is the upper part, and GRACE follow-on has been launched here. And where there are no solutions, this is not because we are lazy or not working. This is because there are no data available, because in particular in the end phase of the GRACE mission, there were a lot of measures to save the battery power to extend the mission as long as possible under certain illumination conditions. And this makes these diagonal stripes here where there are no solutions present. And between GRACE and GRACE follow-on, there was a longer gap of about 1 year where also no of these dedicated mission data are available. What we do in this context is that we try to regularly compare all the different solutions with respect to each other. That's most beneficial because all the different analysis centers will try to do their best in order to improve their individual solutions if there is one solution not so good. And we always address this as the friendly competition, so to say, between the different centers to really go to the maximum and deliver best possible solutions. And of course, we are looking at them on different application levels. What is shown here on the slide, for example, is how the trends for GRACE and GRACE follow-on resulting for Greenland, for example, how they fit together. And we hope to always see pictures like this, where it's shown for the entire Greenland ice sheet, that all the different solutions are hopefully very, very, very close together. That's apparently the case here for Greenland, and this is also confirmed when analyzing the individual basins. You see here that most of these bars are very, very similar, ending up here with this total of about 250 gigatons for the entire Greenland ice sheet. I must also mention that it's not always looking that nice as in Greenland. There are some discrepancies that we are currently trying to resolve. For example, when looking here at the Antarctica, then we see that, for example, in the Western Antarctica part, that's this part here, also the solutions quite nicely line up. But if we go for the eastern part, for example, we indeed see a little bit larger differences between the different input solutions, which will then have at the very end consequences for this combined product that we are deriving, and even has consequences for the entire Antarctica ice shield. Must still say that this is still staying within the error bars, but one sees that there is, on the processing side, a little bit potential for further understanding and improvement. The puzzle has not yet completely solved here. That's something that there is currently being further investigated. I mentioned here this support from the ISI that has been set up, this international team. Actually, this was an activity between 2019 and still ongoing for this year, with a final meeting then January next year, where all these initial cost G structures have been set up, the GRACE release has been computed, and the operational GRACE follow-on release is being computed. Operational means in this terms of GRACE that we have these solutions ready with a delay of 2 to 3 months. So that's operational on this monthly level. Then, without going into details in this presentation, we are doing similar activities also for other missions, for example, for the SWARM mission. There we get some funding from ESA to do this. This is interesting as a gap filler mission. If some of the GRACE follow-on solutions are missing, then that's the best that we can have. That's a mission that is just tracked by GPS, so delivering much lower spatial resolution, but still a real measurement of a monthly snapshot of the Earth's gravity field. And we will extend all this that's currently being ongoing, namely towards China. I already mentioned that there are these 5 Chinese analysis centers. We would like to try to incorporate their solutions in our activities and to strengthen the collaboration with those. And therefore, we initiated in January 2020. This was actually just the week before really the COVID pandemic got viral, so to say, where the Chinese colleagues still could travel to Bern. And this was a very good event for us because thanks of the presence here at the University of Bern, we were able to initiate the collaboration, and this collaboration has ended up in this COSG Chinese ISI team that we have, sponsored by ISI Beijing, also for this year and for the next year. And the last initiative, I already mentioned it briefly, is this currently ongoing European initiative in the frame of Horizon 2020, where on the technical side, we will work on further optimization and operationalization in the COSG workflow within G3P, this initiative. But the main science goal is, of course, another one, because this is not really science, this is operational work. Namely that we would like to explore, or a large consortium would like to explore there, whether this information, total water storage, that can only be measured by GRACE follow-on, as mentioned already before, whether it's really possible on a global scale to use these data to separate some of the compartments together with other remote sensing data. And the compartment that is not very well accessible is groundwater, the most important quantity, of course. And in the frame of this initiative that is currently ongoing, a prototype shall be derived for the Copernicus Climate Change Service, where total water storage will be used together with a bunch of other remote sensing data in order to subtract the measurable compartments to isolate this groundwater product. A very interesting and probably also very ambitious endeavor, but it's, in my opinion, very important that one tries to demonstrate on various levels of initiatives about the added value of this total water storage variations. And this brings me also now to the really last part of the presentation, a couple of slides in terms of maybe future missions. As many of you probably know, when one speaks about missions, here it's shown for ESA missions, one distinguishes somehow a bit between pure science missions, where totally new concepts or so are demonstrated. And then there are other operational monitoring missions. And for example, in the frame of the ESA missions, These are the so-called Copernicus missions or meteorology missions as well. And Copernicus I would like to address very briefly for a moment, because that's the large Europeans in the Earth observation program. And Europe's eyes on Earth, it's usually addressed, where based on operational missions, these so-called Sentinel missions, various services are operated. Services for the atmosphere, for the oceans, for emergency management, for land monitoring, and also a climate change service. And all these services have the primary, one of the goals is to deliver information which is linked to the so-called essential climate variables. And essential climate variables, that's a framework that is defined by the so-called Global Climate Observing System, GCOS, namely, these are variables that are somehow critical for characterizing the climate system and its changes. And these data provide, at the very end, the empirical evidence that is needed to understand and predict the evolution of the climate, to assess the risks, to create adaptation measures, and to underpin climate services. So that's very important. That's a very important framework. And gravity as a measurable quantity is somehow indirectly linked into various of these variables, of course. And one of them, for example, is groundwater, that has been briefly mentioned before, that is very hard to measure on a global scale. And therefore, it's a good move, I would say, to try to demonstrate if gravity data can contribute in this respect. And since a very short time, we are even in a much better position in this respect now, because relatively recently, it seems that the terrestrial total water storage as a measurable quantity has now also been approved already by GCOS. I think the very last formal step is still pending, but we believe, or hope at least, that it is rather a formality, and that very soon at some point in this picture here also total water storage will then appear as an ECV. And an ECV is always a very good motivation or justifications for new missions to measure interesting things. And by this, we believe that in the future, hopefully, we will at some point be able to bring in gravity in these Copernicus services. It's to some extent a bit missing at the moment, a missing link in the Copernicus Earth observation program. And as now being established as an ECV, chances, I believe, are somehow better in the distant future, probably still, but nevertheless, because as all communities, we have to think about how to continue always. And we have seen this picture at the beginning of the talk about all the dedicated gravity missions. At the moment, we are at GRACE follow-on, and of course, the community is organizing in partnership between NASA, ESA, and again, Germany, to have potential follow-up missions. Several studies are currently being ongoing because there is strong belief that there's a strong need for sustained observations. And who knows, maybe at some point we will see what the future gravity missions will be, maybe in the form of a Sentinel mission in the frame of this European Union's framework Earth observation program. This would be one of the visions that we have. Of course, in parallel, also many other scenarios are being followed, but with the help of these European and international initiatives, we believe that we somehow contribute a bit to really make gravity observations to a mature product that belongs to such a large Earth observation program. And with this, I think I'm at the end of my presentation. I would like to thank you very much for your attention.
Thank you very, very much, Adrian. This was really a very, very interesting insight, which really made the connection between the basis of the physical basis and really the application that is really at the frontier of science, and of course, which has a very high importance in all the relation to climate change and to the water budget. Thank you very, very much. So with that, it's time to open a little bit the floor. When you have questions, there are two possibilities. Either you can raise the hand and then you can unmute yourself if you have a question, or you can also write a question directly into the chat. there is no question, I let you think a little bit more, because I have a lot of them. And the first one is, there is a question from Tillman. Would a swarm or network of satellites be feasible? I was actually thinking the same.
Yes, so try to comment a bit on this. Yes, of course, yes. One of the main problems of the GRACE and GRACE follow-on missions is that it is just one pair of satellites. And this has various also negative consequences. I did not go into the details in this respect here, but for example, the entire error characteristics of these solutions is not isotropic. So there are favorable directions in the flight directions and less favorable directions in the cross-track. And one of the largest benefits would be to have more pairs of satellites. So in this respect, yes, a constellation of various pairs would be very beneficial. And basically all the future next generation gravity mission studies go exactly in this direction. And at the very end, it's of course somehow always a question of costs, etc. Of course, you would like to have as many pairs as possible in cleverly selected inclinations and orbits, etc. But already a second pair, or maybe even as there are various scenarios that are currently being studied, for example, have one pair, and an interesting one is also having a second satellite in a cross-track separation and measuring somehow cross-track information. So there are various studies. At the moment, where basically 3 studies are currently ongoing. There is a study from ESA, where a next generation gravity mission is being studied. There are NASA's next generation gravity missions, and there is a particular proposal also from the French Space Agency, where various of these concepts are currently being studied.
Tillman has a follow-up question. Could they fly at lower altitude to improve resolution?
Yes, they could they could do this, and most probably will also be the case for future missions. Problems with lower altitude is always that some other effects are increasing. So there is more drag, for example, affecting the satellite motions, and most probably this will then be scenarios with drag compensation, so drag-free flight, for example. A concept that has already been employed for the GOCE mission, where for the static gravity field determination, the satellite was flying at a very low orbital altitude with just 250 kilometers. And if you want to stay there for a longer time, then you need to do something. Otherwise, you will just decrease and decrease, and the mission will be very short at the very end. But yes, altitude is a very crucial factor. I showed implicitly, I showed it a little bit, but not addressed it in detail in the spherical harmonic expansion that I showed very quickly at the beginning. There is a nasty factor, which is the attenuation of the gravity signal. And this attenuation is a potential law, meaning that all the higher degrees, which are the most interesting ones, because they are the short spatial scales, are very much attenuated if you are too high, and you will have much more sensitivity if you are going down, of course.
Thank you, Adrian. The next question is from Annie. She wrote into the chat. So thanks, Adrian, for this very interesting presentation. I fully agree that the Copernicus program should have a GRACE type mission. My question is about the instrumental payload. Annie, do you want to maybe on GRACE and GRACE follow-up? As you may know, the mean global sea level picture cannot be closed since 2016. Do you think the GRACE problem could be the case? Merci, Annie. Please unmute yourself, please.
Can you hear me?
Yes.
Yes.
So because I got my question is the chat, I use this people it means problem, but I don't know the problem of the failure of the accelerometers is the basis of my question. So apparently for the Greenland and Antarctica mass loss, it seems that it has no effect. But for the global mean sea level, as you may know, we are not able to close the budget for the recent years. So apparently it's not due to altimetry. There is a contribution from Argo via the salinity, but once this problem is taken into account, we still have a gap between the observed global mean sea level and the sum of components. So what about growth? This is my question.
It's of course a very difficult question. I guess the answer no one currently really knows, I believe. And grace people, of course, always tend, I guess every community says always the problem is not on their side.
Yes.
Grace people always tend to say that they believe, or no, they are sure that their technique is somehow bias-free in the sense that it's not doing an absolute measurement, but just a relative measurement. And as far as I know, most of the studies tend to believe that there is no unexplainable bias between, let's say, grace and grace follow-on. But to be totally sure, I think we cannot really be. It's striking that this somehow seems to coincide with the phase where there are also instrument problem on the grace follow-on side, as you mentioned. And I didn't address it here in this talk, but there is one issue, if you like, on the grace follow-on mission, that one of the accelerometers is underperforming, and therefore one needs to transplant, is the process called, the data from the good accelerometer instrument from one satellite to the other satellite. And this, of course, has some danger. I cannot answer you whether this might somehow contribute to this puzzle or not. I mean, what the case is that some of the coefficients that are determined by grace follow-on, some of the very low degree coefficients, they are bad, and therefore they need to be replaced from other techniques like satellite laser ranging. I don't know if there could such an issue somehow come into the play. It would then not be directly grace that is responsible, but these replacement coefficients. But I don't have the evidence now to say this could really be the case or not, so I'm just speculating. So if we will find out at some point, we will let you know, of course, but I don't know. À suivre, yes.
More questions, please. Yeah, à suivre. Definitely. Maybe I can then, if there is at the moment no other question, but you can of course still ask. I was thinking, are there other effects that could maybe also be detected, changes in the mass distribution on Earth than water? I mean, maybe the timescales and the resolution, because it's typically large resolution, is limiting it. But of course, there are lava flows in the interior. There is vegetation growing and disappearing again. Is that something which could at some point be in reach?
I think people are indeed also looking at interior Earth applications, but as you mentioned, there usually the timescales are quite different. But that's definitely something where studies are ongoing. I can maybe also mention that large earthquakes or so, the changes in the mass redistribution can indeed be seen in these data. And I didn't address this here in any detail or so, but there are a lot of effects that also, in principle, there is sensitivity, but needs to be reduced. For example, all the atmospheric effects or oceanic effects, they are basically on much shorter timescales that they can be detected in a reliable way by grace. And therefore, one uses their other data to measure these and to compute the impact on gravity and to reduce it from the signal in order to not produce aliasing effects. So there is sensitivity to a large range in principle, but most of the variations which are of sufficient magnitude and also of reasonable spatial scales that they are detectable, these are in the vicinity of the Earth. Yeah, basically the water movements.
Any more questions, please? If not, I still have one. I mean, you mentioned already the impact of drag. I imagine this is relatively complicated. So this is something you just said that you don't measure directly, but you'd rather take it from other measurements and you try to correct for it.
Yes.
Okay.
Yes. So I can quickly follow up on this a bit. I also did not mention it explicitly. All these dedicated gravity missions, they are all equipped with onboard accelerometers. So these are measurement devices which measure the sum of all the non-gravitational forces acting on a satellite with really superb precision. So the best ones ever being built so far were those flying on the GOCE mission, and one has there some spectacular 10 to minus 12 or so meters per second square. But all these instruments, they are also not able, so far at least, all the instruments, they have also not yet the possibility to measure in an absolute sense. So they need to be calibrated somehow. And calibration means that also some of the effects like bias and scales and maybe some instrument drifts or so need them to be derived from the data. But one uses this as additional empirically measured information and feeds it into the recovery process. And by this, one can basically separate or try to the extent possible to separate the non-gravitational from the gravitational forces.
Okay.
And therefore, exactly in the case of GRACE follow-on, this is a bit more challenging because, as I said, one of these instruments is not showing the full performance as one would have liked it. Yes.
And now you're using that basically as a correction. Could there be also an application of these results, or is that not the case?
Yes. I mean, these are very important data also for other disciplines. For example, the entire thermosphere modeling or so. Their missions equipped with high quality accelerometer data, they are crucial as input in order to feed these models, because there it's really a very complicated problem with a very bad coverage measurements and huge gaps, because you don't have too many satellites which are really having these high quality devices. So yes, for these kind of models, for atmospheric models, this is very important.
Okay, interesting. I see that Tillman has another question. He says, would it be possible to see effects of plate tectonics after our plates are moving at millimeters per year, maybe over the time of the mission?
Yeah, I think that, well, that I would say there are better tech. Well, in principle, somehow, yes. I mean, what you see, it's not plate tectonic, but what I mentioned as an example is this land uplift. And this is a bit more than a millimeter per year. This is even going up to centimeters per year or so. And then we are in the range of the detectability of GRACE. But for plate tectonics, there are better techniques. So for example, terrestrial GNSS data, GPS networks or so, they are very well suited to really precisely measure these millimeter per year vectors. Because one always has to remind that GRACE is a technology that feels the entire impact of all the ongoing changes on the Earth. So it cannot really locate the changes very precisely because it has this limited resolution. And that's the big difference to other remote sensing techniques, which just look down and make a picture or a radar picture or whatever, and can precisely geolocate it. And GRACE has more difficulties to do the geolocation. So therefore, for this example here, a more geometry-oriented technique are the best techniques to see these things.
I still have also another question. I mean, you talked about the GPS satellites, but you mentioned also there are other systems like GLONASS and also now the European Galileo. I was a little bit wondering, what is their role, given that you have also these laser links which give these incredible precision. Do these different positioning systems play a role still, or could you do the research basically also without them?
In order, you could not do it without them, because you need somehow to have an absolute leveling, so to say. This needs not to be ultra precise, but nevertheless, in the centimeter regions or so, this is possible. And without the GPS products, for example, and the GPS constellations, you could simply not do it. So you could not process really the GRACE data without any GPS or similar. But of course, the actual information at the very end does not come from there, or the main information or the main sensitivity comes from these inter-satellite measurements. And there, the contribution of GPS really to their derived time variations or so, this is rather limited. Okay. One can do studies in this direction, and it's also being done and tried to be exploited. What can be done with GPS alone, and it's quite fascinating. When I started my PhD, this was not possible, and meanwhile one can do it also reasonably well somehow, but it's really confined then to the very large scale structures. So the long wavelengths part, even of the Earth's time variable fields, can be delivered by GPS tracking of these satellites, but not really much more. And for this, GPS is simply not precise enough. I mean, the phase observable has millimeter precision, and that's simply another order of magnitude than these inter-satellite measurements.
I still have one last, maybe. Tilman mentioned that a swarm of satellites, and of course now you have all these commercial missions, which I think we are not, as astronomers at least, not so happy with that, but they do launch huge swarms of satellites. Yeah. And my question is a little bit, if we have that, is there at least a way of making use of it? Maybe for such an application?
That's an interesting question. I was just being aware 1 month ago that there was an ESA call for Spire data. Spire is one of these large constellations. And Spire is a mission that they offer dual frequency GPS receivers on board of relatively good high quality. And of course, we made an attempt to get these data just because it's interesting and potentially really interesting for many scientific applications in our domain, including to some extent probably also the Earth's gravity field a little bit, but mainly for phases where there is no GRACE data or so available, if there is no other information. And then one can profit a lot indeed when having just many satellites. If GRACE-like missions or even future gravity missions with very dedicated concepts are available, even hundreds of GPS-tracked satellites will not help you enough with the current precision that GPS data have. But one should take into account that it's a bit interesting that you have a very dense coverage. Nevertheless, that's then the big advantage. And some of the effects need to be reduced in the current GRACE processing, and maybe they could contribute to these de-aliasing products. So they have maybe a certain application, but needs to be tested and simulated or studied with real data. But if it will indeed be the case that some of these commercial operators disclose their data also for scientists, for example, it will be interesting for many applications. I believe, yes.
Okay. I think it's now 7:45. I think if there is no other question, I would like to slowly close our meeting. And of course, I would like to thank Adrian again very much. For the members of ProEC, you're going to be informed soon about the next talk, which will probably already be relatively soon. And again, let us thank Adrian very much for the talk. Thank you very much, Adrian.
You're welcome. Thanks a lot.